Hello everyone and welcome back. In the previous video we've seen a two-layer neural network learning a simple text dataset trying to predict the next token from the last one. Now we are scaling to a sequence length of 20 characters, so we are taking quite a bit of context and trying to predict the next single character. Our dataset looks something like this, with 20 integer values as inputs and 1 as output. We will obviously use one-hot encoding like before to make it easier for the model to understand the meaning of those integer values. And we also need an added step because the input size is scaled by sequence length. We need 20 times the input that we had before because we have 20 times the characters. We also need another step during the training loop because we have sequence length times of characters basically, and we need to flatten the shape to be one-dimensional. Anyway, these are the rough changes and the performance has improved a lot. We went from 2.5 to 2.1, so it's much better, but it's taking a while. 43 seconds is quite a lot, and that's because if we take a look at the shapes of all of the layers, the weights of the first one are extremely big with more than 100,000 parameters. The linear layers scale with sequence length times vocabulary size times hidden size because of these three parameters. They are all multiplied together. Now, both sequence length and hidden size determine the performance of the model, and vocabulary size is the only one that we can work on. If you think about the one-hot encoding, it's extremely inefficient because it's encoding very little information in a very high-dimensional discrete tensor that's also very sparse. What we can do is reduce that dimension, make it continuous and dense, so that in less space we can store more information. The actual implementation of this idea looks like this. We are making a bunch of different arrays of size embedding size, one for each character that can appear in the training set. So each character has its own little embedding vector that is trained and tries to learn the character's meaning. This is how we apply it in the training loop. We just index through the embeddings using the integer values in the batch inputs, and we flatten them like before. The performance has not become that much worse. It's a tiny bit worse. We were getting 2.1, this is 2.2. But the training time is better than half, is less than half, about a third. Now that we understand most of the components that we are going to use to train bigger networks, we can abstract all of these concepts away and use PyTorch modules that are more reusable and easier to scale. This is how we build a model with an end-dot module. We first initialized the model like this with all of the required arguments, and these inside of the initialization are all the parameters that the model is going to work with. We have embeddings like before and two linear layers. The biases are embedded into the linear layers, as you can see, bias is true by default. Then in the forward pass, we have this very simple system where we call self.embeddings, we call self.w1 and w2, and they just work. They are extremely simple. This is the flatten from before written in less space, and we have an activation function here. Forward is called like this by using the model that we initialized here and just calling it as if it was a function. It works even better than our equivalent implementation by hand because they have better initializations and all around better code than what we do. Now that we transitioned all of our code to NN module, we can very easily move the model on the GPU, which are devices intended for gaming, but they are so powerful that they are really useful for fast parallel execution, like what we do with machine learning. So we move the model to the device, and we also do the same for the inputs and labels. As you can see, I also increased the number of steps, and we are able to train in basically the same time for much longer and get better performance. If you take a look at some predictions, they look quite decent actually. The model is producing words that make sense. The spacings are reasonable. The length of the paragraphs is not the same that we had here, and especially the number of lines in each paragraph is not the same, because we don't have enough context length with the 20 characters, and the model is having a rough time understanding at what point of the sentence it is. What we can do now is scale the model in all directions, starting with adding more layers. The code up to here is the same. We load the dataset, and then we initialize this new model with this module list of linear layers that's called hidden. Basically, these are hidden layers, and it's easily configurable through these arguments like hidden size and number of layers. In the forward pass, we just iterate over a fully connected hidden, and we apply value after the linear layer, basically resetting the value of x at each iteration of over the hidden layers. We are also wrapping the training loop in this train function, so that it's going to be easier to rerun later in the code, because we are going to iterate on the architecture quite a lot in this section. The performance is quite a bit better than before, achieving 1.8 in less time than it took the one on the GPU. So if a couple of hidden layers are so powerful, let's try to add many more of them. With the 20 layers, we reinitialize the network and we retrain it. As you can see, the code is extremely simple because we already set up everything before, but the model is not training well. The loss is worse than before and it's taking a while. What's the problem here? When we are applying the linear layers, we are resetting the value of x each time, and the information is having trouble going through the forward and backward pass through all of those interruptions in the layers. We need to change the architecture a little bit so that the gradients have a quick way of being transferred to the previous layers. And a very elegant way to do this is, instead of resetting the value of x with the one after the linear layer, we just increment the value of x. So the model is taking 20 steps, 20 layers, to consecutively update and refine the hidden state, which is stored inside x, until we get to the output. And as you can see, we are getting a loss of 1.5, which is extremely good, and we can continue scaling. Let's try 56 layers. Again, extremely short script, and we are getting a starting loss which is extremely high. The problem here is that when you have many multiplications in a series, the mean of the value of x over time is going to either decrease exponentially or increase exponentially. Right now it's trying to increase, and we have a couple of solutions for this. We either nail the initializations perfectly, which is boring and math intensive, or we force the mean and standard deviations to be reasonable over the length of the model. So we are introducing layer normalizations, which are a very simple way to control the mean and standard deviation at wherever they are called. So we are putting a different layer norm before each hidden layer. And the result of this is a loss of 1.3. So the model is able to train effectively without gradients or basically hidden state blowing up. Looking at some predictions, they look even better than before, with multiple words in a series making sense. But you might wonder what happens when we go extremely crazy with the number of layers. The model doesn't get that much better, we get extremely diminishing returns, but we are able to eke out a bit more performance, which is always nice. But the training time is blowing up. Actually, there is not only this dimension of scaling, because we've tried to increase the number of layers, but we totally ignored the width of the layers. So let's try scaling by a factor of 4 both the embedding size and the hidden size, leaving 10 layers. The performance of this model is extraordinarily good in a very short amount of time. But as you can see here, the validation loss is not as good. This is called overfitting, when the model is big enough that is able to memorize the training set and do really well on the training set, while performing a bit worse on data points that it's never seen before. Throughout all of the deep MLPs that we've worked with here, there has always been this awkward step after the embeddings where we flatten out all of the context into a big vector that we pass to the first layer. Here there is no reuse in parameters, and there is a very rudimentary notion of the character position in the sequence. A more elegant way of approaching the sequence scaling problem is with RNNs. An RNN looks something like this. We have a hidden state initialized at 0, and it gets updated in 2 ways. At each step, it receives an update from the input through a linear layer, and then it's transformed into the next hidden state through another linear layer. And it gets through this couple of steps for many times as the inputs, consecutively updating its value through its previous version and the new inputs. In the end, we take the final hidden state and we use a linear layer to extract the next character prediction. This system has far better parameter reuse, since every input is processed by the same linear layer, and it has an intrinsic notion of basically the position of each element in a sequence. The code looks something like this. We have the 3 linear layers and the hidden state initialized at 0, and for each time step we take the element of the sequence and update the state with the input and the previous hidden state. In the end, we have the final linear layer that extracts the output from the hidden state. The training loop looks exactly the same as before, and the performance is pretty decent at around 2, which is equivalent to a basically 2-layer MLP. But the loss is extremely noisy, even with a Gaussian filter applied on the plot. A pretty big improvement that's actually quite fascinating is multi-token training. I previously said that we are using an output layer to extract the next token from the last step. What if we extracted the next token at each step? Since the hidden state only has context on the tokens of the past, we can try to predict the next token at each time step, which results in an extremely big improvement in the number of tokens trained per step. This adds very little compute requirements, because we are running more times the output layer, so it's around 50% slower, but the performance is quite a bit better with a loss of 1.8 and extremely smooth loss function. Now, an interesting thing to do would be to try all of the sequence lengths with the increments of 2 and see if the performance improves by increasing the number of elements that the model has as context. As you can see, with a sequence length of 1, it quickly levels off without being able to train much more, while longer sequence lengths are able to extract more information from each training step, and they are getting better performance and also leveling off far slower. So they could potentially get way better performance. This is the plot with the validation loss instead of the training loss, and these are the two overlaid together. Thanks for watching, and see you in the next section talking about the transformer.